He's Ming, and he's a PhD student in our department of National Taiwan University. And he's going to tell us about his new work, titled General One Particle Effective Field Theory Potential and Black Hole as the Elementary Particle.
So thank you for the introduction. So first, let me give you some overviews. And so this work is starting from this black hole in spiral motion, and in our formulation, it can be considered as a massive spinning particles scattering with multiple exchange of gravitons. And in this work, since the black holes are very far apart, so and we know that when black holes are outside the event horizon, it can only be characterized by its mass, charge, and spin. So for our purpose, black holes act like point particles, and so I will later give a better description of this statement. And usually, when we think about black holes, we usually describe them with coordinate-dependent metrics. So is it possible for us to give a purely onshore description of black holes? And if so, then and if this is all true, then we can describe the black hole interactions as scattering amplitudes. Okay, so let me first get into the formalism that I'll be using in this work. So usually we can write the momenta as a product of two spinners. And here, since the particle outside here are massive, so it should be attached the SU2 index to it. And from the covariance of the amplitudes, we can write the amplitude as something that carries two SU2 indices with all the indices symmetrized, parameterizing all the possible polarizations of the spinning particle. And when we strip off these external massive spinners, and we are left with a symmetrized SL2C tensor. So now, if we want to write down what this is, we just need to find a two linear independent two-component spinners to span this space. And so first, let me get into the case where these two are massive and this is massless. And first, this is M1 and this is M2, so they have different masses. So the natural basis one can use is this. But something will be quite different when the mass becomes degenerate. So from the three-particle kinematics, we can see that P1, this P1 dot P3 will equal to 0. And so that the basis on the last page here will no longer be linear independent. So now we need to switch to other things that carries all these SL2C indices. And now we are only left with two choices. One is this Lebesgue beta, and the other is this lambda. And because of this degeneracy, we will introduce a proportionality factor x right here, and where this x carries +1 helicity of this massless particle. So after this setup, we are ready to write down the most general amplitude, 3-point amplitude of this interaction. So the first one here is the minimal coupling, and it's just purely x. And these, and since they will correspond to higher derivative terms, and so they are higher dimensional operators. So what is special about this minimal coupling? So if we take the high energy limit, one will see that it will just give us the massless amplitudes. So that it has a good high energy behavior. Where all of these things, they have 1/n scalings, so they will just blow up in the higher energy limit. So so they are higher dimensional operators. And finally, so we can write down so we're mostly concerning about this. this plus helicity minimal coupling amplitude or minus helicity minimal coupling amplitude. So let me give you another example of this formalism. So which will be of use in the last part of my talk, and which is these two are masters and this one is massive. And so and here the linear independent basis basically becomes this becomes lambda of the first particle and lambda of the second particles. And in general, such amplitude will look like this. So by little group covariance, one can uniquely determine the coefficients A, B, and C here, so that this amplitude is completely fixed by the Poincare symmetry. So okay, so let me talk about what is the relation between minimal coupling and black holes. So if you look at the one particle effective action of black holes, then you will see that it consists of three parts. One of them is the universal part where it is coupling to momentum. And here it is coupling the minimal coupling to spin. And then there are all these these higher dimensional operators with Wilson coefficients C. And for Kerr black holes, it was shown that these Wilson coefficients are just 1. So one can just translate these into our spinor variables. So the whole amplitude just will just look like this. Okay, and this is the expression from the last page. And for our minimal coupling amplitudes, it just look like this. So by converting them into the similar form, and one can extract the coefficient here, this CABS and this CABS tilde, where this for black hole, this is just simply 1. And so when we compare both of them, one will see that they are equivalent to each other up to this 1 over S scaling, where S is just the spin of the particle. So we conclude that minimal coupling amplitude just corresponds to Kerr black holes in the infinite spin limits. That's the relation between this particle, this minimal coupling amplitude and black holes. And so what does that imply? So the first implication is that black holes has no Kerr. So because as I showed you several pages ago, this amplitude it should have 2s plus 1 terms, and these coefficients are unknown. But now we see from this connection that all this G1 to G2s coefficients are just 0 in the infinite spin limit, and leaving just the minimal coupling. So that we have no way to characterize black holes by this G1 and G2 to G2s. So that it reflects that this is the most simple amplitude, and so we conclude that this is our way of saying that black holes has no Kerr. Okay. So one thing that we can do is the in-spiral motion. We can extract the potential from of the in-spiral motion, which in our formalism, this is just this diagram exchanging multiple gravitons, and so from the amplitude, and then we just need to divide it by 4EAEB, so and it will give us the correct classical potential, and we are. So here we are mostly concerned with the so we are mostly concerned with this one graviton exchange, which is just a tree process, and two graviton exchange, which is just a one loop process. And for the tree process, this amplitude is just like multiplying the 2 3 points here together, and where the amplitude just looked like this, where the classical potential will in general look like this expression. So with this identification of the spins, so one can simply extract this Bij coefficient, so that it is just the classical potential of the 1 p.m. black hole. And okay, so what about 2 p.m. where this is just two graviton exchange? So in general, one needs to compute the full one loop amplitude. But since we are only interested in the classical limits, and we know that any one loop amplitude can be decomposed into a bubble, a triangle, and a box. And only this integral will give us the classical behavior of this amplitude. So all we are concerned with is just this diagram, it's just this cut. So here we just need to insert the known minimal coupling amplitudes here, and this is just the content amplitude, which can be constructed from the minimal coupling. If the particle here has spin less or equal than 2, this amplitude will the content will just simply look like this. You can see that there is no 1/n vectors, so that it has a good high energy behavior. And we can also see that when S is larger than 2, this vector comes down to the denominator and becomes a spurious pole. So as an amplitude, it does not make any sense. So we can conclude that there's no fundamental particles for spin larger than 2. Also, this amplitude is constructed by gluing 3 points together. So they are actually polynomial ambiguities since they have no poles. So it is potentially that there are polynomial terms that might ruin the classical potential at 2 p.m. However, since it has no 1/n counting, so the polynomial terms can be separated out just simply by 1/n counting. And for spin larger than 2, one needs to eliminate this spurious behavior, so that the amplitude will generally look like this, where you can see that there are several factors of 1/n here. And also the polynomial ambiguity still remains here, but it is no longer separable by 1/n counting. So we're still trying to figure out what is the way to find the correct polynomial terms for black holes, and that will basically give us the correct 2 p.m. potential. So basically, what I said before are Kerr black holes. So are there any? So can like Kerr-Newman black holes be described in a similar way? The answer is yes. So the Kerr-Schilf form of the Kerr-Newman black hole looks like this, where at asymptotic distance, one can see that this h nu is just this, and a nu is this one. So we can ask that is there a point-like description of Kerr-Newman black holes? So first, let's just focus on this part. For this part, it can be rewritten as this. And since we already know what the gauge field looks like, one can just plug in the Maxwell equation and extract the current associated with it. And so to describe it as a 3-point interaction, so one just need to extract the amplitude from this part, where we actually already have all the elements we needed. And so by translating these variables to our spinor variables, one can see that at the infinite spin limit, it again matches with minimal coupling. So but this time is so minimal coupling describe the Kerr-Newman, the interaction between electric field and the Kerr-Newman black hole, like this. Well, it's just minimal coupling. But that's not the full answer. Here we also have this Q squared piece hiding in this H union. And if you look closer, you will see that there's R squared scaling, which is the leading effect generated by one loop. And since this H union is sourced by this stress tensor, so we can actually just compute the form factors and these form factors, so that we can know if it give us the correct Q squared part of the metric. And here, and since this is G to the first power and Q to the second power, this loop effect can be captured by this diagram, where this is a photon loop, and this line is a charged particle. And so how do we do it in an on-shell way? So since this is basically an off-shell graviton, we can just simply treat it as an on-shell massive spin 2 particle, where this amplitude was already given by this. This interaction, and so by doing this and just substitute the content in the last part of my talk with this amplitude, one can simply extract these form factors, and this is the results from Feynman diagrams. But so far, we have already successfully captured these classical pieces from this amplitude, from this on-shell method. And I think the result will be helpful. So thank you for your attention.
I'm not sure if I understood the motivation. So is the idea to use these on-shell field theory techniques to compute nonlinear effects in this?
Sorry, I'm not sure what you mean by nonlinear effects.
So, well, or put it differently. So what is the basic message? So you use these field theory techniques,
yeah,
and then in the beginning you compared it with the whatever. You have black holes interacting with each other, and you. So what information, what classical information do you get out of this theory computations?
So we're trying to extract two information. One is the classical potential of two scattering black holes, and the other one is this. We are trying to compute we're trying to reproduce the metric, the H mu from the H mu from this amplitude.
So this would be linear or non-linear?
Linear, it's just H to the first.
Yeah.
So it's the gravity quite the kind of general relativity simulation available. I mean, it must be available, right? So are you actually comparing?
Yeah, we are.
So this is a kind of simplified it's a simulation from LIGO for the design of numerical control. You are looking at the two Kerr-Newman black holes scattered off each other.
We're not actually doing Kerr-Newman black holes scattering off each other. We're doing Kerr black holes scattering.
Just Kerr black.
Yeah, the scattering is the Kerr black hole, and we're identifying the metric of the Kerr-Newman black hole from this 3-point interaction.
So the motivation of this program is what? That to show that the scattering for the amplitude method can also reproduce particle gravity.
Yeah.
But is there some possibility that you can see beyond, well, whether it's some deviation from the Einstein gravity in the scattering process?
so far we haven't really seen some C deviations.
Okay, so any more questions for us? Okay, if not, let's thank him and all the speakers. Johnson, any announcements or follow-up?
I think we go for 8. Sometimes I have to wait for.
I think Candy says 6 o'clock plus leaving, and I guess we should get it outside, like around midnight.
Yeah, so it's just 6 o'clock full time stay.
Is that right? Oh, okay then. If people need to go to the toilet, I can tell otherwise.
Go back to your time.
Gracias.